Hello again. Just a couple more sections left in this chapter, not too many. But this one's actually, I always think it's kind of fun. Because you notice all the sections in this chapter so far, we've been dealing with rational expressions, but all we've really done is simplify them. You just say, oh, look at this thing, make it look better. Or add these two rational expressions together, or subtract them, multiply them. So all you're doing is making something complicated look better or simpler. But every time I get to solve an equation, I always feel like I'm actually doing something. I solved a mystery. So that's why I like these sections where you're actually solving an equation. So in this section, like the title suggests, we're going to be solving rational equations. And a rational equation, you can just think of it as it's an equation in which one or more rational expressions are present. But of course, kind of unspoken, remember that equation means there's an equal sign. That's something we haven't seen in this whole chapter so far. So all of a sudden, they'll take one or two or three rational expressions, add them together, multiply them, or subtract them, or whatever. There's going to be some equal sign somewhere in there, so we'll be able to figure out what the variable is equal to, and when we solve it. So it'll be kind of interesting. I like these because I feel like I actually did something. I didn't just clean something up and make it look better. I actually solved it to figure out what x is, or what z is, or whatever variable. Alright, well, let's see. Maybe we'll read over how to solve these guys. It's kind of... Actually, you know what? The method for solving these guys, it kind of reminds me of method 2 for simplifying the complex rational expressions. Remember method 2 that we just learned for complex rational expressions? It was, it said, you calculate the least common denominator of all the little denominators, and then you're going to multiply everything by it. It's not that you want to get all the denominators to have that common denominator, it's that you're using it as a tool to get rid of the denominators. So it's kind of the same idea in this section, which is kind of nice. So maybe I'll even point that out, because sometimes people they'll forget kind of how to do these problems, and they'll just try to get a common denominator between all the fractions, and then they'll get stuck, because it won't help to get a common denominator. So yeah, let me see. I'm going to say LCD is a tool to help us clear all denominators. Because these equations are they're impossible to solve if x, or your variable, is stuck in the denominator. So what we're trying to do is get everything out of the denominator and into the numerator, and then we actually have a chance of actually solving. So LCD, it's a tool to help us clear all denominators. It's not that we want to combine fractions. That's usually what least common denominators are for. They're for, I'm just getting a common denominator so I can add fractions together, or I can subtract fractions. That's not part of the section. That's kind of a waste of time in this section. You could, for example, if you look way down at part D, for some reason that one's kind of making me think this would be something I'd want to do. If I look on the left side, I have two separate rational expressions there. 3 over x minus 3 plus 5 over x plus 2. I might be tempted to think about, a couple sections back we learned how to add those. Let me get a common denominator, make sure they have the same denominator, and combine them into one. But really, in this section, that would be a waste of time. That's not really going to help. It might make it a little simpler looking, but it really will not help you solve this equation. So don't try to combine fractions into one. It's kind of, like I said, it's kind of a waste of time. It seems like a good idea. It'll make it look simpler, but it won't help us solve. We have to follow the steps in this section. Okay, so first thing, Step 1 says, list any restrictions on the solutions, any value of the variable which causes the denominator to be 0. I don't know if you remember, but way back in the first section of this chapter, we were kind of studying rational expressions. We learned how to reduce rational expressions, but the other thing was we wanted to see if you're given a rational expression, are there any values, or is there one value or more than one values that will make the denominator 0? So that's the first thing you want to do. Like, for example, if I look at part A here, I want to see when will any denominator, if I had more than one, I'd look at all of them. When will a denominator equal 0? Will that ever happen? Well, in this first example, part A, I only have one fraction there, 4 over y. The other guys are kind of whole numbers. So really all I have to do is say, when will that denominator be 0? And if you remember, all you do is you take the denominator and you set it equal to 0. Kind of like thinking of this as an equation. Denominator equals 0. Well, the denominator is y. So So when that equals 0, that's when I'll get a 0 denominator, of course. If y is 0, that fraction would be 4 over 0. And that would be a problem. So I have to make a note of that first. That I guess the thing is, if I were to solve this equation and I got a solution of 0, say, what if 0 was a solution? Then I'd have to throw it out because 0 is not really a solution because it's going to make the equation undefined. So it's kind of like, yeah, in the very beginning you say, all right, what are the values I cannot have in my solutions? I'm going to write them down, and then when I get my solution or solutions, I'm going to make sure this guy's not in there. So that's what I'll do at the very end when I actually solve it. Make sure y equals 0 is not a solution when I'm done. It's hard to remember that because all the steps of solving it, you're going to, it's easy to forget. You're like, okay, finally I'm done with this stupid problem. But you really got to be sure or be careful and say, wait, was that one value that I found that the denominator could not be? Is that in my solutions? Okay, I better throw it out. Okay, so we did that. That's the first step. And then step 2 says what? You want to calculate the least common denominator of all the rational expressions within the equation. But again, in this one we got lucky. There's only one denominator. It's y. So I think that would be the LCD, right? If there's only one denominator, that guy has the common denominator. Okay, so that's step 2. We kind of did step 1 up here. Step 2's done. Okay, now step 3. Now we're on step 3. What does it say? You want to multiply each term on both sides of the equation by the LCD. So like I said, it really reminds me of what we did in the previous section where we take the LCD, like ours is y, okay. We're going to take it and multiply it by every term in the equation. So I always write it in parentheses or brackets, or outside parentheses or brackets, and then I rewrite the equation inside. And then just distribute that y onto everything, or whatever the common denominator is. So it's y, the LCD, times all 3 terms, the 2 that are on the left and the 1 that's on the right. So you can't skip any. You're not just multiplying it by the terms that are fractions or rational expressions. You have to multiply it by every single term. And let me see, what are we going to get there? Then it's, so y times y first, that's y squared. And then we'll have y times 4 over y. If you want to be careful, it's not a bad idea to write that out, and then see what happens. So it's the y, I'm distributing this y, and writing it next to the 4 over y to see what happens. That guy times 4 over y. Alright, just to be careful. Lastly though, then you do y times negative 5. I think I can handle that. That's negative 5y. There we go. Okay, I think so far so good. Everything's kind of a whole number. There's no fractions left except this guy. I'm going to have to put this y over 1 in order to multiply across. But before I do, I notice the y's cancel. So really that term just becomes a 4. So it's y squared, the first term there, plus 4, because that's really all you get out of that term, equals negative 5y, because that's what's on the other side. Whew. And then once there are no denominators, it's much more clear how to solve it. So this guy, it kind of looks like one of those problems from the previous chapter where we had to use factoring to solve an equation. But remember, if you want to use the product of, the zero product property, or the property of zero products, if you want to use that to factor and solve an equation, you have to have all your terms on one side. And so since one of my terms is on the wrong side, I want to move the 5y over so he's on the same side as everybody else. Add the 5y. Okay, and then of course you always want things in descending order of powers. So I'll write the y squared first, then the 5y, and then the 4. And now 0's on the right side. Alright, let me rewrite this guy real quick. Y squared plus 5y plus 4. And now we want to see if this factors. Well, it's a trinomial with leading coefficient 1, so it should be the easy factoring method. I just have to figure out, okay, what are these numbers that multiply to 4 but add up to 5? Well, that'd be 4 and 1, or 1 and 4. Plus 1 plus 4 plus 4 plus 1, whichever way you want to think of it. And now that I have it factored, now the last step would be set each factor equal to 0. So y plus 4 equals 0, y plus 1 equals 0. And then I'll solve each one separately. To solve the first one, I subtract 4 from both sides, and I'll get y equals negative 4. And the other guy, I'll subtract 1 from both sides, and that'll give me y equals negative 1. There we go. So there are 2 solutions. And I should, like it said, the whole point of the first step was you have to be sure that that number that you found that was a bad value, make sure that's not in your answer. But notice, what was it? It was y equals 0. If that was one of my solutions, then I would throw it out. But we got -4 and 1. We're good. We don't need to throw those away. Those are perfect. It's only if one of them was 0, I'd throw it out. Like say the first one was 0, y equals 0. I'd throw him out, and the only solution would be the other guy, y equals -1. Okay, but since the value we found in step 1 wasn't in our solution anyway, I guess we didn't have to worry about it, but you do have to do step 1 just in case. Man, if you notice, these problems, they take a while, right? It's kind of a lot of steps to it. But the more you do it, the more you get the hang of it. It's a lot of steps. So let's try part B now. Okay, part B. Okay, the first thing we're supposed to do is think of, are there any values of x, or your variable, that would make the denominator 0? So when would either, and we have two denominators here, when would either denominator equal 0? So we have to think about it. Let me set the first denominator equal to 0 and think about that. The second denominator equal to 0. But that's never going to happen, right? There's no variable, so there's no way x equals something will influence whether those denominators are 0 or not. This is never going to happen, either of them. 5 will never equal 0. 4 will never equal 0. So really, step 1 doesn't matter in this one. There's no value of x that'll make the denominator 0. So I wouldn't have to worry about it actually in this one. Thankfully. So whatever solution or solutions I get, I won't have to throw anything away. Okay, that was step 1. Now we'll do step 2. Step 2 is to calculate the least common denominator of all the denominators. There's only two denominators, right? 5 and 4. Those guys, their common denominator, is 20. Alright, and again, it's easy to mistake it and think, oh, I'm finding the common denominator so I can combine fractions into 1. No, you're not really trying to combine fractions, you're trying to get rid of fractions, or get rid of denominators. So now that I've calculated the common denominator, step 3 is take that LCD, which is 20, and multiply it by every term in the equation. So I'll go 20 times the x plus 2 over 5, the first term, 20 times the -1, which is the second term, and the 20 times the x minus 2 over 4, which is the third term. I'll distribute that guy. Let's see, 20 times that guy, 20 times that guy, 20 times that guy. And just to be safe, like I said before, I'm going to write 20 next to the fractions. 20 times x plus 2 over 5. I think the second one, though, I don't have to write that out. 20 times -1, that's just -20. So that one I don't think I have to be too careful on. But I think the 20 multiplied by the fraction on the right side, I'm going to be careful. It's 20 times, that fraction is x minus 2 over 4. Alright, we'll see what happens here. So as we've seen a lot of times, I'm going to have to write the 20 over 1 in both cases where they're green. That way I can see what reduces. So on the very left one, I noticed the 5 can go into the 20 4 times. So really you're left with the 4 there, times the x plus 2 that was there. And be careful, you have to put that in parentheses, because the 4 is meant to be multiplied by this entire numerator, both terms, not just one. And the minus 20, there wasn't much to do with that guy. We're just going to keep him the same. On the other side now, I'm going to see what cancels. This 4 can go into 25 times. So kind of similar to the first one, I have 5 times parentheses because there are two terms there, x minus 2. And again, that's because this 5 is meant to be multiplied by this entire numerator, not just one term, but the x and the 2. Alright, now this looks like a much better equation. I'm much more excited to solve this. I think what I would do first is, you don't want to see any parentheses in your equation, so I distribute the 4 here, and distribute the 5 here, and then we'll see what happens from there. If I distribute the 4, I'll get 4x plus 8, and then there's the minus 20 that's kind of been waiting for everything else. And then if I distribute the 5, I'll have 5x minus 10. I have a few like terms on the left side here. 4x, 8 and -20 makes -12. Okay, so far so good. And looking at this guy, you don't see any x squared terms, right? You notice it's just an x on either side. This one I can tell that there's no need to factor. I won't need to get everything on one side and factor, because there's no term with a higher power than 1, Yeah, so since I only see constants and x's, no x squareds or x to the third or anything like that, no need to factor. This is kind of like, I could just solve this the old-fashioned way like we learned in, chapter 1 or chapter 2. let me bring that guy over here so I can see it better. It's 4x minus 12 equals 5x minus 10. If I want to isolate x, I'm going to move the 4x over to the right side, minus 4x, excuse me. And that way negative 12 will be all by himself on the left side. 5x minus 4x is just x, or 1x. And then you get the minus 10 there. We'll be done if I just move that 10 over, because then x will be isolated. If I add 10 to the other side, I'll get negative 2 equals x. Alright, that must be the solution. So you notice in the last example we got 2 solutions, and this one we only got 1. That's fine. Sometimes you'll get 2, sometimes you'll get 1, sometimes you'll get 3. If you're unlucky, I guess. That must mean it's a really complicated problem. And I should at this point go back and say, oh, in step 1, what value or values of x did I have to throw away? But I remember there were none, right? We said, oh, there are no values of x that I have to throw away, so x equals negative 2 must be a good solution. There it is. And of course you can check it if you want to check it. Let's see. Any of these can be checked. In the first example, remember we got 2 solutions, so you have to actually check both, one at a time. But if you want to, let's see, what was this guy? He was x plus 2 over 5 minus 1 equals x minus 2 over 4. So I think my solution was x equals negative 2. I'm going to replace both x's with negative 2 and see if I get a true statement there. Alright, so if there's an x in the numerator there, minus 1 equals, and an x in this numerator here, okay, well here it's negative 2 plus 2, that's 0 over 5, minus 1 equals, negative 2 minus 2 is negative 4 over 4. On the left side, 0 over 5 is 0. So you're just left with negative 1. On the right side, actually, negative 4 divided by 4 is negative 1. That's true. Negative 1 is equal to negative 1. So that must mean we got the right solution. But if I got anything that wasn't true, like 0 equals 5 or negative 1 equals negative 7, that would mean I got the wrong solution, and I better check my work. Sometimes it's easy to make a mistake, too. All those steps in these problems, just imagine, it's easy to make, do one little thing wrong. Ugh. Anyway, alright, let's look at part C now. Where's that guy? Here he is. Alright. It looks kind of simple. It's only got 1 fraction equals 1 fraction. There's only 2 terms there. But let me see. The first step I'm supposed to do, is I'm supposed to check to see, are there any values that would make either denominator undefined? Or either fraction undefined. But that would mean I want to see when the denominator is 0. So I'm going to take each denominator. The first one's n minus 3. I'm going to see when he's equal to 0. The second one's n minus 2. I'm going to see when he's equal to 0. Let me see. I'll solve the first one. What is that guy? He is n minus 3. Okay, I have to add 3 to the other side to solve it. So I guess I find that n equals 3. That would be a bad value because, yeah, that makes sense too. If you put 3 here for n, 3 minus 3 is 0. That's bad. So it does make sense that that's a value I don't want to see. So when I'm finally done with this problem, I better make sure that 3 is not a solution. If it is, I'm throwing it out and either I have no solution or I only have one, the other one. If I want to solve the second one, n minus 2 equals 0, I'll add 2 to the other side. So it looks like n equals 2 is the other one. So I got to try to remember that. It's easy to forget at the very end when you're done that you want to check. So in the end, I want to make sure that in the end my solution, I have n not equal to 3 and n not equal to 2. Those better not be solutions. If they are, I'm throwing them out. It's hard to remember that, but I'll try to remember. Okay, that was step 1. Now, step 2 is to calculate the least common denominator. Alright, so I notice one denominator is n minus 3. It's kind of a complicated denominator, right? And so is the other one, n minus 2. If I want to calculate the least common denominator of these kind of complicated denominators, I'm supposed to first factor them. But they don't factor, right? N minus 3 is too simple, so is n minus 2. So they don't factor. So I guess I'm thinking each of them is their own factor. N minus 3 is one factor, so my LCD needs that. And n minus 2 is a factor. So my LCD also needs that as well. So really that's the LCD, n minus 3 and n minus 2. Okay, now the next step is I want to take that and multiply it on both sides. Because that's the whole point, is find the LCD so that you can multiply the whole equation by it, and it should cancel all the denominators. So I'm taking that big crazy LCD, n minus 3, n minus 2, multiplying it by the fraction on the left and the fraction on the right. That should be interesting. But I'm going to be careful. I'm going to do like we did before and kind of write it out. N minus 3, n minus 2. I'm going to multiply that, or, you know, write it next to the first fraction there. N plus 2 over n minus 3 equals, okay, now I'm going to write that. I'm also distributing the n minus 3, n minus 2, the LCD, onto the fraction on the right. So I'm going to write that guy next to the fraction on the right. N plus 1 over n minus 2. Let's see. Oops, shoot. I'm going to get rid of a little bit of this so that you can see it better. It was n not equal to 3, n not equal to 2, just so that's not taking up too much room. And we have n plus 1 here over n minus 2. Okay. Looks good. Alright, now if I'm looking, kind of focusing on the left side there, the left side of the equal sign. I want to see if that reduces, but I better put this over 1 so I can see what reduces. Same thing on the right. But on the left side, I notice n minus 3's cancel on the diagonal, right? But that's about all that cancels, so I'd be left with, once I cancel, n minus 2 on the top, times the n plus 2 that's also on the top. But there's nothing left on the denominator, so it's really a 1, but you don't really have to write the 1. You could just say, oh, everything canceled from the denominator, so it's nothing. Okay. How about in the second, the fraction on the right? I noticed the n minus 3's cancel on the diagonal, right? Or sorry, n minus 2's. n minus 2, n minus 2. So what's left in the numerator is the n minus 3 times the n plus 1 that was in the fraction to begin with. And I'm definitely putting this n plus 1 in parentheses because, again, it's meant to be this whole n minus 3 is multiplied by this whole n plus 1, the entire thing. Alright, now if I want to solve this, I have a lot of things to distribute. Actually, if I want to distribute things and multiply things out, I'm going to actually have to FOIL over here. Do first times first, outer times outer, inner times inner, last times last. And actually the same thing on the right side as well. This is kind of a complicated problem, huh? But I think if we're careful, it's going to work out fine. Let's see, so I'll FOIL the left side. First times first, n times n, that's n squared. Outer times outer, n times 2 is 2n. And then inner times inner, negative 2 times n is negative 2n. Negative 2 times 2 is the last, which is negative 4. Okay, and I think I'm just going to combine those right now. I notice 2n minus 2n is nothing. All you're left with is the first, n squared, and the last, negative 4. Alright, how about on the right side? First times first, n times n is n squared. Outer times outer, n times 1 is just n, or 1n if you want. And then inner times inner, negative 3 times n, negative 3n. The last times the last, negative 3 times 1 is negative 3. There we go. Alright, what are my like terms here? N squared has no like term, but the n and the negative 3n can make negative 2n. And then you got the minus 3. Whew! Alright. Now I see that there are n squareds on both sides, and there's an n on the right side. But probably what I'll have to do is get everything on one side and try to factor, I'd imagine. And in this one, you know, we said you're supposed to get everything on the side that'll make the highest powered term positive. But these guys, they both have... I mean, I think if I move either one to the other side so they get together, they're going to cancel, right? Like, let's say I subtract this n squared to move it over. N squared, it's actually just going to cancel with this n squared. So I was, you know, at first I thought, oh, I probably have to factor this, so let me get everything on one side. But as I started to get everything on one side, I realized, wait, the n squareds are going to cancel. And now that there's no n squared, there's only an n and constants, I realize I don't have to factor, as a matter of fact. I can just kind of isolate n. That's nice. And n, okay, he's here. Might as well start isolating him. I'm first going to move the 3 over. That'll probably be the first step to try to get n by itself. That'll make the left side negative 1. The right side now is just negative 2n. Okay, and the last step would be divide both sides by that coefficient, negative 2. Okay, so we got n. N is all by itself now. Where we go? Here we go. It's equal to this guy. Negative 1 over negative 2, that's positive 1 over 2. So 1/2. Whew! I thought we might get 2 solutions because it was so complicated, but we only got 1. And I just got to check, were either of those values we said were bad part of my solution? No. Okay, I didn't see a 3 or a 2. Whew, good thing. So we can keep that solution. He's a good solution. Ooh, that was a tricky one, huh? But it was kind of fun in a way. In a weird way. Alright, let's try part D. This one looks even more complicated, but I think it's going to be fine. Alright, looking at that guy. Whew! I'm looking at that guy. He's crazy. The first step is I'm supposed to see if any denominator is going to be 0, and if so, when would that happen? What x value would make that denominator 0? Let's see, I'm going to erase all this junk over here so I have room to think about that. And this one's going to be a lot of work for step 1 because this guy has 3 fractions, so I have to think about each of their denominators being 0. Step 1, when is a denominator equal to 0? So I got 3 of them. The very left one is denominator's x minus 3. I gotta figure out when he's 0. The middle one's x plus 2. I gotta figure out when he's 0. The last one, x squared minus x minus 6. I gotta figure out when he's 0 as well. Whew, okay. Well, I'm gonna look at the left one. It's x minus 3 equals 0. I'll solve it by adding 3 to both sides. It looks like 3 is the value I don't want. Same as the last one, huh? And the second guy, I'm going to subtract 2 from both sides to solve it. I'll find that x equals negative 2 is another value I definitely do not want in my solution. The very rightmost one, this is something so complicated that I can't just isolate x. I'm going to have to factor this guy to solve it. And I notice I already have all my terms on one side, right? A 0 on the other, so there's no need to move anything around. It's already in the right form, so I'm just going to factor it. And it's a trinomial with leading coefficient 1, so I could just do the easy factoring method. I just have to figure out what are the numbers that multiply to negative 6 and add up to negative 1. I think those guys would be negative 3 and positive 2. Or the other way around, positive 2, negative 3. And now that we factored it, I'll set each factor equal to 0. Man, this is crazy. But you notice both of these factors, they're the same as what we were solving here. X minus 3 equals 0. Now we're solving that again here. And we're getting 3. So I already found that number. There was no need to do this sort of. I didn't realize it at the time, but I've already decided I'm not going to let the solution be 3 or negative 2. And actually, these are the values we're getting again. So these are kind of redundant. It's like, here I've already decided I want to make sure that the solution is not 3 or negative 2. And I thought I was finding more values here, but it was actually the same values in disguise. So really, it's just 3 and negative 2 that I need to worry about. These guys produce the same values anyway. But that doesn't always happen, so you really do have to check all the denominators just to be safe. Okay. And that seems like a lot of work, but you know what you could actually do if you want? It's like the first one, we set the denominator equal to 0 and solve for x. But you know what you could do is just say, what could you put for x to get 0? Like, what minus 3 equals 0? Well, 3, right? 3 minus 3 equals 0. So that's the value you don't want there. And kind of similarly for the second one, you say, what plus 2 is 0? What can you add to 2 to get 0? Well, it'd be negative 2, right? Negative 2 plus 2 is 0. That means that's the value I don't want. So you could, if you wanted to, not even show this work here. Just kind of do it in your head for the simpler denominators. Because those denominators are so simple that you might be able to just guess kind of like that. What can I subtract 3 from and get 0? What can I add 2 to get 0? But that third denominator, I don't think I could have done that. That's kind of tricky. What can you square, and then subtract the number from it, and then subtract 6 and get 0? Okay, that's too complicated. That's where I probably would have had to actually write it out and solve it. For sure. Alright, so whatever happens, I better make sure that my answer does not contain a 3 or a negative 2. So I remind myself by putting a not equal to. It's not like I want those to be the solutions. I want to make sure those are not the solutions. So the next step now is to figure out what the least common denominator is. And this is one where, since the third denominator is so complicated, it's too hard to calculate the LCD the way it is. I'm going to factor all the denominators first. When the first denominator is too simple to be factored, so is the second. For the third one, we already factored it on the right side when we were solving it. I can kind of copy my work. It was x minus 3x plus 2. Alright, that's going to make calculating the least common denominator a lot easier. And now that I look at them, okay, we said the LCD should contain any factors you see between them. So the first denominator, I see an x minus 3. I need that in my LCD. The second fraction, I see a x plus 2 in the denominator. But looking at the third denominator, I already have those two things, x minus 3 and x plus 2. So it'll be kind of redundant to include those again. And for both of them, the most number of times I see them is once. I only see it once in the first, once in the second, and once each in the third. So I really only need one of each. And now I might as well multiply it by both of those, or all three of those terms. So that's the third step, is to distribute this guy. So this whole thing, x minus 3x plus 2, is going to multiply by the first fraction, the second, and the third. And this one I think I'm going to be really careful. I'm going to write that LCD next to each one. So x minus 3, x plus 2. First he's being distributed onto the first fraction, the 3 over x minus 3. And I'll see what happens with him. And then I'm going to distribute the x minus 3, x plus 2 onto the second fraction, okay, which is 5 over x plus 2. Okay, and then lastly, on the other side, that common denominator, x minus 3, x plus 2, is being multiplied by that fraction as well, 5x over... And remember we said when you do everything like this, you want to leave it in factored form. So I'd still keep the denominator here, x minus 3x plus 2. I wouldn't go back to the original denominator, because everything's better when it's in factored form. It's going to make everything easier. And it's clear now because I can see what cancels more. And so if I want to see what reduces, I better put each of these over 1, and then I can see what reduces. For the left one, I've got this guy times this guy. Along the diagonal, x minus 3's cancel. But you're left with, okay, the x plus 2 times the 3 that was in the numerator there. Okay, that's all that's left though. Oops, sorry. Times 3 plus, okay, now on the next one, what cancels? I see x plus 2 cancels with x plus 2. So you're left with the x minus 3 factor that was there times the 5 that was in the numerator there. Alright, let's see. Now on the other side of the equal sign, actually everything cancels from that diagonal. X minus 3's cancel and x plus 2's cancel. So you're really just left with the numerator that was there, 5x. So that's pretty good. Alright, I think this is fairly simple looking, I think. And especially if I distribute. If I want to solve for x, I'm definitely going to have to distribute this 3 in here. And then this 5 in here. Let's see, and you know what? If you think that's kind of weird, I think we're used to distributing from the left. If you want, you can rewrite it. I'm going to write the 3 on the left. Sometimes that helps. And then same thing with this guy. I'm going to write the 5 on the left. I don't know. I think that just makes me feel more comfortable. Like, I'm used to distributing from the left. Alright, if I distribute the 3 in there, that'll make that 3x plus 6. If I distribute this 5 in here, it'll be 5x minus 15. And then on the right, there's nothing to do. It's only one term. Alright, now on the left side, I see that there are a couple like terms. 3x and 5x are like terms. Together they can make 8x. The other like terms are the 6 and the negative 15. They make negative 9. And then on the other side, the 5x is kind of just sitting there waiting to see what happens. Alright, now what? I want to get the x's together. So it's up to you which side you want to bring them on. I just think moving the 8x to the right side is going to be faster. Because then you have the x terms together and the constant term on the other side. So negative 9's now all by himself equals 5x minus 8x would be negative 3x. And I'll finish this problem off by dividing both sides by negative 3. And that'll give us, we only have one solution. It's x equals 3. Okay, yeah, because negative 9 over negative 3 is 3. But now I have to be safe and go back to step 1 and see if that was one of the values that we had to throw out. Let's see, where was that? Uh-oh, it is, right? Look at that guy. X cannot be 3. So from step 1, I'm kind of reminding myself here. X cannot be 3. That means since that was our only solution and we have to throw it out, there's no solution. Which makes me very sad because I feel like I just wasted a bunch of time. It's like they sent me on a wild goose chase, you know? The people in the book or the people from the homework, they made up this problem knowing there's no solution, and they're laughing at me right now because I spent all that time trying to solve something that has no solution. Thanks, guys. Oh, what a bunch of poopy heads, am I right? Sheesh. Anyway, that doesn't always happen, but I just wanted to do one where there's no solution. That way, in case you come across one, you won't freak out and say, What does that mean? That's not possible. Unfortunately, it is possible. It's sad but true. Alright, let's try this next one. This one looks kind of fun. It looks cuter or simpler than the other one, but, you know, we'll see. You never know. These guys are kind of crazy. Alright, so this guy, part E. I'm looking at this guy. Remember, the first thing you want to do, step 1, is to figure out when would any denominator equal 0. Would that ever happen? And this guy, since there are two denominators, I'm going to set each one of those equal to 0. We got t minus 3, the first one, I'm going to see when he's equal to 0. And then the other guy is t squared minus 9. When is he equal to 0? Alright. Let's see here. Well, the first one is pretty simple to solve. You just move the 3 over. And now that I think about it, this might be one of those ones that you could have just said, look at the denominator and say, what minus 3 is 0? Oh, 3. So anyway, I don't know if you really had to do all that, but there it is. Seems like 3 is always a bad number in all these problems, huh? It's like the first step always results in don't have 3 in your answer. It's funny. But okay, now if we want to solve the second guy, we want to set the set the denominator equal to 0. T squared minus 9 equals 0. That's one we actually have to factor. All the terms are on one side, so we don't have to worry about that. But this is a difference of squares. T minus 3, t plus 3. And if I set each of those factors equal to 0, t minus 3 equals 0, t plus 3 equals 0. Okay, I can solve each of those. I'm going to here subtract 3, or sorry, add 3, and here subtract 3. So we'll get t equals 3, which is actually something we already knew. We already had that here, so that's nothing new. But this one's a new one. T equals negative 3. Okay, so we found out there are two values we don't want. T cannot equal 3, and then t cannot equal negative 3. So I got to remember that for when I'm done. Make sure that my solution doesn't include 3 or negative 3. I'll have to throw either of those out, or both. Phew. Okay, sounds good. That was step 1. Now let's see. Step 2 is to find the LCD. But I think, again, the LCD, you're only able to find it if you factored all the denominators that can be factored. So I'm going to look at the first fraction. The denominator can't be factored. It's too simple. T minus 3, that's it. But the second one, we've already seen above that t squared minus 9 factors into t minus 3, t plus 3. So feel free to use your same work you already did, Why refactor that when you've already done it above in this step here? Alright, now that I'm looking at that, I think I can calculate the LCD. See, what factors do I see there? Between the two denominators, I see a t minus 3, and I see a t plus 3, but that's really it between them. And the most number of times I see a t minus 3 is once. They both only have 1, so I just need 1, because I just take the greater. And then t plus 3 I only see once. So that's pretty much it. I'm just going to take that t minus 3, t plus 3, multiply it by the entire equation. I'm going to distribute that whole thing, this whole big crazy LCD, onto the first fraction, onto the second fraction, and onto the 1 on the other side. Don't forget about that guy. So even if part of it is not a fraction, like there's a term that's a whole number, you still have to multiply it by that LCD. Oops, what the heck? Huh. Alright then, let me see. So first I'm distributing the t minus 3, t plus 3 onto the first fraction, which was 5 over t minus 3. Okay, and I'll see what happens with him. There's a subtraction sign. And then I'm distributing the t minus 3, t plus 3 onto the second fraction, which is 30 over that t minus 3, t plus 3. Whew. And then on the other side as well, we're multiplying the 1 by that common denominator. It's also distributing onto that one, t minus 3, t plus 3. Holy moly. That's a lot. Whew. So this 1, yeah, just carried down. It's being distributed upon now. This fraction carried down and this fraction carried down. Just kind of writing the thing in the front next to each of those three things. The first fraction, the second fraction, and the 1. And now for each of the fractions, we got to put the t minus 3, t plus 3 over 1 and see what reduces. I don't need to do it to the last one because there's no fraction. I'm just able to multiply everything out. But for the very left factors, I see that the t minus 3's across the diagonal cancel. After that, you'll be left with the 5, which I'm going to put in the front. Because remember last time we put that number on the right side and then we switched it anyway. 5 times t plus 3, because if two things are being multiplied, it doesn't matter what order they're in, you can switch them around. And then in the second, let's see, the second fraction's being multiplied, I see that both cancel, right? T minus 3 and t plus 3. So really all that's left is the minus 30. Because he's the only guy left there. Huh, interesting. And then on the right side, I see it's t minus 3, t plus 3 times 1. But anything times 1 is that thing, so I don't think I really need the 1. I'm just going to leave it off. Yeah, well, like we said, 1 times anything is that thing. There's no need to rewrite it. Alright, I think we're looking good now. Now I'm probably going to distribute everything I can. First this 5. 5 times t and then 5 times 3. That'll be 5t plus 15 and then minus this 30 here. Over here I'm going to have to FOIL this out. T times t is t squared. T times 3 is 3t. Negative 3 times t is negative 3t. Negative 3 times 3 is minus 9. And if I combine like terms, actually those 3 t's cancel, right? And I should have known that because t squared minus 9 is what we started with, and that's how it factored, you know? So we're going backwards. We factored it, we're just going backwards to what it used to be. Oh well. On the left side, there are 2 like terms. 15 minus 30 is negative 15. Okay, looking good so far. And now what? Okay. I see that there's a t squared term here and a t term here. So I would not be able to just isolate t. You know, I can't get t by itself since it's occurring twice in 2 separate terms that aren't like terms. So what I'm going to have to do is get all the terms on one side and try to factor it. But to determine which side to bring everything on, remember you want the term with the highest power, this guy, to stay positive. So if I were to move everything to the left side, he would become negative because I'd have to subtract t squared, and then it would be a negative t squared on the left. And that's not good. It's too hard to factor when the leading term is negative. So I'm going to make everybody else move to the right. Minus 5t over to the right, plus the 15 over to the right. That's going to work better. Alright, and since we're running out of room, I'm going to kind of write the result down here. Nothing's on the left side now because 5t's gone, 15's gone. 0 equals t squared is the only guy with a square. The negative 5t is the only term with a t. But you have some like terms here. The negative 9 and the 15 make 6. Okay, now that I have everything on one side, I'm going to try to factor this guy. And I think this factors into, the easy factoring technique because it's a trinomial with leading coefficient 1. It's a t and a t. I have to figure out what multiplies to positive 6 but adds up to negative 5. It would be negative 3 and negative 2. Because negative 3 times negative 2 is positive 6. Negative 3 plus negative 2 is negative 5. If you were thinking 6 and 1, it wouldn't work because if you had to do, like, say, negative 6 times 1, that would add up to negative 5, but it would not multiply to positive 6. It would multiply to negative 6. Well, yeah, like we said before, there are a lot of times where it seems like one factorization is the right thing, but it doesn't quite work out because of the signs. Alright, now we're almost done. Now if I set each of these equal to 0, each factor, t minus 3 equals 0, t minus 2 equals 0. If I solve, let's see, the first one, I would add 3 to both sides. Let's see here. Add 3, add 3. Alright, so I'll have t equals 3. Actually, in the back of my mind, I remember that was a value I can't have. So I know I'm throwing him out. This one, I'll add 2 to both sides to solve him, and I'll find that t equals 2. Alright, so I would have 2 solutions, except, remember at the top in step 1 we said t cannot equal 3. So I have to throw him out. The other one was t equals negative 3, but I don't have a negative 3. I don't have to worry about that. Although I did have to throw one solution out, I get to keep the other one. Because that wasn't one of the bad values that we found in the first step. So it's kind of strange. You can think you have 2 solutions, but when you kind of check it to make sure it's an okay value, it turns out you can only have 1 solution. But there are a lot of times where you get 2 solutions and you could get to keep both. I think like in the first example we did, part A, that's how it happened, I think. We got 2 solutions, oops, sorry. Yeah, and we got to keep both. Whew, this one, part F, it looks pretty like a doozy, huh? This guy looks pretty crazy. So I'm looking at that one, woo, hello, oh my gosh. You know what we could actually do if you're, for step 1 we're trying to figure out where is this thing undefined. Especially for people that are fairly savvy at math and they like to not take so much time. I think the first thing I'll do is I'm going to factor all denominators, and that might make it easier to see what values make the denominator 0. I think that's what I'll do first. Factor denominators. Okay, so the first one, it's x squared plus 3x minus 4. That factors into x plus 4x minus 1, because it's a trinomial with leading coefficient 1. Plus, the second fraction has x plus 1 over x squared plus 6x plus 8. So I'm just looking for what numbers multiply to 8 but add to 6. 4 and 2, or 2 and 4, whatever. There we go. On the other side, it's a similar thing. I'm looking for what numbers multiply to negative 2 but add up to positive 1. It would be 2 and negative 1. Or the other way around. You know what you can actually do is just think, like in each individual factor, say, like in here, x plus 4. What value of x would make that 0? So what can you add with 4 to get 0? It'd be negative 4, right? Negative 4 plus 4 would be 0. So you've kind of taken care of that factor. How about the second factor? What minus 1 is 0? What can you subtract 1 from to get 0? Well, that'd be a 1, right? I'm kind of keeping track of these values here. And that guy's taken care of. The next factor I see in the second fraction, x plus 4, I've already seen that guy. And we know that x equals negative 4 is the one that makes that 0. So there's no need to do it again. I've already figured that out. The next guy, x plus 2, I ask myself, what plus 2 is 0? That would be negative 2, right? Negative 2 plus 2 is 0. And then the next factor, x plus 2, I've already done that. What plus 2 equals 0? That would be negative 2. We got that guy. The very last one, x plus 1 equals 0. I've actually done that as well. That was here, 1, because 1 minus 1 is 0. So that's one way you could do it. If you want, just factor all the denominators, and then think of each individual factor and just ask yourself, what could go in that little factor to make that little factor 0? So it kind of helps. But if you don't like that, you say, wait, that's too much. I don't know, too much. You can always take each of those off to the side and factor them. You know, like go, take the first guy, it was x plus 4, x minus 1. What if I set that equal to 0, and then you're going to set this factor equal to 0, the other factor equal to 0, and solve it. You know, solve. And you're going to do the same thing with the second one. You got to take that guy, set him equal to 0, which means you're going to set each factor equal to 0, blah, blah, blah. Anyway, by the time you're done, you're going to get only these 3 values. So, I don't know, it's not that big a deal, you know. You could do it the fast way like we just did, or do it the long way. But I kind of like the fast way because these problems are already long enough as it is. You're going to get so burnt out doing all these problems. Just really helps to have a nice, quick way to do things. Alright, now that we have all that, I think I need to calculate the LCD now. That's the second step. Because that was the first step. Okay, second step, LCD. And I've already factored all the denominators, so that's kind of going to be helpful. The LCD, okay, what I need to do is grab any factor I see between the denominators. I see an x plus 4, I see an x minus 1, and I see an x plus 2. But I think those are the only factors that are in any of these denominators, right? And each of those factors only occurs at most once. I never see any of those more than once. Like here, we got a 1 power, 1 power, 1 power, 1 power, 1 power, 1 power. It never occurs more than once, so I really only need one of each. And I'm going to multiply that by each of the fractions that I had in this problem. I'm going to distribute it onto this guy, onto the second fraction, and onto the fraction on the other side here. And it's going to look like a mess, but it's going to look a lot better once we kind of cancel things. It's going to be, oh my gosh, it's going to get way better. So I'm going to take that whole, all 3 of those terms, distribute it onto the first fraction, onto the second, and onto the third. Whew, and it's going to get, this problem's going to get really wide over here. So okay, first it's x plus 4, x minus 1, x plus 2. That whole LCD times the first fraction, I'm going to write it next to him, times x over x plus 4, x minus 4, or sorry, x minus 1, plus, alright, now I'm going to write that whole crazy thing, LCD next to the second fraction if I have room, x plus 2, oh my gosh, this is crazy, huh? Times the second fraction, where is he? X plus 1 over x plus 4, x plus 2, oh my gosh, and then the other side, same thing. Oh my goodness. This is getting crazy. All 3 factors, x plus 4, x minus 1, x plus 2, times the last fraction, which was 2x over x plus 2, x minus 1. Oh my goodness. This is where it's like, if you were doing this problem on your homework or something, you might just change your paper from portrait to landscape orientation, huh? Crazy. Oh my gosh, look at that crazy mess. It's okay though. Now look at the very left. I'm going to have to put all this over 1 to see what reduces. But you know what? A lot of it reduces. Notice on the diagonal, x plus 4s cancel and x plus 1s cancel. So really all that's left is the x that was in the numerator. I'm going to write him on the left because it'll be easier to distribute. Oops. Sorry, the x here, this guy, times the x plus 2 that I didn't cancel from that factor. So that's really all that's left from that first term there. That's not bad, right? Alright, how about the second one? Now I'm going to put this guy over 1 as well. And I notice the x plus 4s cancel, right? And then the x plus 2s cancel. But you're left with, okay, the x plus 1, or sorry, the x minus 1 factor from the LCD times the x plus 1 that was in the numerator. Whew! Alright, how about the last guy? I'm going to put that whole thing over 1. And what cancels there? The x plus 2 cancels, the x minus 1 cancels, but that x plus 4 is left to be multiplied by the 2x that's in this numerator. 2x times the x plus 4. Holy shamoly. So the step, notice the step above was so bad. I was thinking, oh my gosh, how is this problem getting better? But look how nice it is down below this line I drew. Oh my gosh, it's so much nicer. So even though it looks crazy, it looks tedious, it's going to be, it's going to be fine. Okay, and before we finish solving this, I just want to point out, if you thought, oh my gosh, that's crazy, we have to write all that out. If you're, like I said before, if you're really math savvy, or you kind of like to skip steps, up here at this stage that I highlighted, you know what you could have done is like say, okay, because this is how I usually do it actually in my head. Now that I've done a lot of these problems in my life, I look and say, first I'm going to multiply this LCD by the first fraction. And I just look at the diagonal and I say, what's going to cancel there? X plus 4's cancel, x minus 1's cancel, so what's left? The x times the x plus 2. And you can just skip right down to this step right here without even writing this out at all. And then do the same thing for the next fraction. You're taking this whole LCD, x plus 4, x minus 1, x plus 2, multiplying it by the second fraction. I can see that the x plus 4's cancel on the diagonal, the x plus 2's cancel on the diagonal, but the x minus 1 is left to be multiplied by the x plus 1. And that'll bring you down to this stage. And anyway, on and on and on. You can just kind of look at what cancels and see what's left over. So if you wanted to, you could skip this whole steps of writing that out. If you're really careful. So I would probably, if this is a new kind of concept, I would do it the long way a couple times at least, and then see if you can do it the short way like that, just to be safe, because you never know. Okay, now back to the problem. You can finish this problem off. I think I'm going to have to distribute some stuff though. Here, distribute the x in will give you x squared plus 2x. Here I'll have to FOIL it out. The first times the first, x times x is x squared. Outer, x times 1 is x. Inner times inner is a negative x. The last times the last is a negative 1. On the other side, if I distribute the 2x, I'll get 2x squared plus 8x. Alright, let's see, like terms. What do we have? On the left, actually these x's cancel, right? There are some x squareds in common. I'm going to combine them. X squared plus x squared makes 2x squared. Plus, then there's a 2x here, and there's a negative 1 also on that side. I think we got it all. The x squareds combined to make this 2x squared. The 2x we brought down, the 1 we brought down. Okay, so everything from the left side of the equation is taken care of. The right side, there are no like terms. 2x squared plus 8x. So this looks complicated, and I'm thinking, oh man, look at there's x squared terms and x terms. This will be one of those cases where we have to move everything to one side and factor. But you know what? Once you move everything to one side, let's say I move this 2x squared over here and the 8x over there. That way there's nothing on the right side. I notice that the x squared terms actually cancel, right? 2x squared minus 2x squared is nothing. So it's going to become a problem where I don't have to factor because there's no more x squared term left. So I've got, then there's 2x minus 8x, that's negative 6x. And then the minus 1 that was already there. I've moved everything over from the right side, so there's nothing on the right side. This is a nice problem, not too bad to solve, right? I have to first move the 1 over. If I move the 1 over, then negative 6x equals positive 1. And the last step would be divide both sides by negative 6. Whew! This has been a lot of work for one little measly solution here. Negative 1/6. Oh my gosh, really? All that work just for that guy? Ah! But I should make sure that that's not one of the values we got from step 1. We didn't, huh? Step 1 we got negative 4, 1, and negative 2. But I don't have that value in my solution, so I'm good. I get to keep this guy. Whew, that was bad. Oh my gosh. I know it seemed like a lot of work, a lot of writing, but yeah, the better you get at these, the more steps you can skip. And it'll be less writing and more, I don't know. Yeah, a lot less hectic, I guess is the word I'm thinking of. Man. Alright, that was pretty bad. Hopefully you're sort of getting the hang of it. It's complicated, but at least the idea makes sense, I hope. The first thing you do, make sure no denominator will ever be 0. Then take the LCD and multiply it by everyone. So it's good. The main thing is try to memorize the steps, because as long as you have the steps down, even if you make little mistakes here or there, even if you don't get the right solution, what I'm really looking for is, do you have the idea of how to do it? I'm not as concerned with the actual solution as I am with, yeah, did you actually memorize the steps? Do you remember how the process works? If you get the wrong answer, I'll mark you off a couple points, but I'm not as worried about that as I am the steps, Alright, last one. Whew! Let's look at this guy. I'm gonna do like we did in the last one, where if I want to see what value or values would make the denominator 0. I'm going to factor all denominators I can, and then I might be able to just kind of eyeball it and see what they are. The first denominator, that's one of those simple factoring techniques since it's a trinomial with leading coefficient 1. Let's see, what times what makes 3 but adds up to 4? 3 and 1. Or 1 and 3, whatever. But the second fraction, the denominator can't factor, it's already simple. And same thing with the one on the other side, a plus 1, it's as simple as it gets. But now I just look at it and I say, alright, step 1, and what if I were to set this guy equal to 0? Or what if I said, what could I place in there for a to make that 0? What plus 3 is 0? That'd be negative 3, right? Negative 3 plus 3 would be 0. That must be a bad value. What about the next factor? What could I put in there, add 1 to it, and get 0? What plus 1 is 0? Negative 1. That makes sense. Negative 1 plus 1, yeah, 0. And this guy, a plus 3, I've already seen that. I've already figured out what could I add 3 to get 0. Same thing with this guy, a plus 1, I've already taken care of that over here. So it must be that negative 3 and 1 are the ones I don't want to see in my answer. So when I'm done, I better make sure negative 1 or negative 3 is not a solution. Alright, done step 1. Seems a lot easier now, I think, right, than the way we did it before. But I think it's because we've done so many of these and we kind of get the hang of it by now. I think it's easier. Alright, now we want to calculate the least common denominator. I think it's going to be similar to the previous one because I know my LCD should contain every factor I see in the denominators. I see an a plus 3 in the first denominator as well as an a plus 1. In the second denominator there's an a plus 3, but I've already included that. Same thing with the a plus 1 in the third denominator. And the most number of times I see either of those is once. There's only one here, one here, one here, one there. So I really only need one of each. Now that I have the LCD, I'm going to distribute it onto the first fraction, onto the second, and onto the third. And if you want, you can cancel as we go. So how about, I'm going to cancel as we go just to show how fast it could be, but if you're not comfortable, then I'll cross it off and do it the long way just to be safe. Okay, so think about it this way. I'm going to multiply the LCD, a plus 3, a plus 1 times the first fraction. But notice that both of these cancel on the diagonal, a plus 3, a plus 1. So you'd really only be left with 5 minus 3a for that term. And then there's a minus sign. Okay, now when I multiply a plus 3 times a plus 3, a plus 1 times the second fraction, the a plus 3's cancel, but not the a plus 1, so he's still there. And this 2a plus 2 is still there. The numerator, 2a plus 2, a plus 1. Because again, let's see, this a plus 3 canceled here, but the a plus 1 did not cancel, that's why he's still here. And this numerator is still here. Alright, so if that makes sense, and you can do that, then feel free to skip the step of writing the LCD next to each fraction and then reducing. Alright, then the last one you've got, if I were to multiply this a plus 3, a plus 1 by the last fraction, the a plus 1s would cancel, but that a plus 3 would be left over from the LCD as well as the 3 minus a. Well, you could just skip right to that if you wanted to. So feel free, but I'm gonna now erase that just because, yeah, I don't want anyone to feel like, oh my gosh, that was too much. I'd rather be safe, and do it the longer way, but the more careful way. Yeah, okay, let me erase all that crap. I'm gonna write this guy again. He got too messed up. Oops, he was a plus 3, a plus 1. Alright, so let me see. I'm gonna write him next to the first fraction. But we're just taking an extra step that's longer than the way I just wrote it. Alright, that times the first fraction. Alright, then there's a minus sign. Now I'm multiplying by that LCD by the second fraction. A plus 3, a plus 1 times. The second fraction is 2a plus 2 over a plus 3. Okay, then there's an equal sign. The LCD, a plus 3, a plus 1 times the last fraction, which is this guy here, 3 minus a over a plus 1. Alright. Now I think if I put each of those LCDs over 1, I can see what reduces in each case. On the very left side, I see the a plus 3s and the a plus 1s cancel. So I'm left with that numerator, 5 minus 3a. Okay, and then there's a subtraction sign. For the second fraction, I see that the a plus 3's cancel, but a plus 1 and 2 2a plus 2 are left over. So I'm going to write that guy, those guys next to each other. A plus 1. I'm going to put the 2a plus 2 in parentheses, even though it's not that way in the numerator. Because when I multiply these guys, they're really meant to be multiplied fully together. A plus 1, the whole thing, times 2a plus 2, the whole thing. And in the very last fraction, I see that the a plus 1s cancel on the diagonal. But the a plus 3 is left over, and the 3 minus a that was in the numerator is left over. And similarly, he's not in parentheses, but I better put him in parentheses because it was meant to have this whole thing and this whole thing multiplied together. Whew! Alright, it looks complicated, somewhat complicated still, but at least there's no denominators left. I like that. Let's see now. I'm going to multiply everything I can out and FOIL, kind of. Here, 5 minus 3a, there's nothing really to do with that yet. I'm going to be really careful here, because when I have a minus sign here, or a subtraction sign, it's meant for this entire thing, whatever it is. So when I FOIL that out, I'm going to keep it in parentheses. You got to be really careful, again, because if you FOIL it without leaving it in parentheses, you're only giving this subtraction sign to the first term, when it actually should be given to every term that results from FOILing this. So be really careful. Let me FOIL that out. A times 2a would be 2a squared. A times 2 is 2a. 1 times 2a is another 2a. 1 times 2 is 2. And on the other side I'm going to FOIL that out as well. A times 3 is 3a, that's the first times the first. The outer times the outer, a times negative a is negative a squared. The inner times the inner, 3 times 3 is 9. And the last times the last, 3 times negative a is negative 3a. Whew! On the left side over here, let's see, I think, I'm just going to be careful. I got a 5 minus 3a. I'm going to distribute this minus onto everybody here. Minus 2a squared, minus 2a, minus 2a, minus 2. And then I'll combine like terms later. On the right side, I see that there are a couple like terms, but the 3a's cancel. 3a minus 3a is nothing. So I'm left with the negative a squared plus 9. Okay, on the left side, the 2a squared, negative 2a squared, that's the highest power and it has no one to combine with. So I'll just write him as is. But then for the a's, I have a negative 3a, a negative 2a, and another negative 2a. So let's see, negative 3 and negative 2 makes negative 5. Negative 5 minus 2 is negative 7. So okay, it must be negative 7a for the next term. So I got that. The constant terms, there's one in the front, 5, and one in the back, negative 2. So 5 minus 2, that's going to be 3. So plus 3, since it's positive. Whew, alright. And on the right side, we've already combined any like terms we could. Negative a squared plus 9. Whew. Okay. And looking at the equation we're left with now, I notice that there's a term with a in it. I see it here, 7a. And there's a term with a squared in it on either side. Since there's a's and a squareds, I'm going to have to get everything on one side and factor. And so, okay, to determine which side to bring everything on, I'm going to see which side would make the leading term, which is here, a squared and a squared. If I brought things on one side or the other, which side would I bring them on to make sure he's positive? Let me see. Well, imagine, what if I move this a squared over here? I'd add it because it's negative. But here, if I move it, okay, what's that? Negative 2a squared plus a squared, it's still negative a squared. That's not good because he's negative. I think I want to move everything the other way. I'm going to move everything from the left side to the right side. And because if I move that 2a squared, I'd add it. And now if I add those guys together, what's that? Negative a squared and 2a squared is 1a squared. That's positive. So that's how I know I'm moving it the right direction. Alright, so I moved him over. I also have to move the 7a over. Since it's negative, I'll add it. And this 3 I have to move over as well. Since it's positive, I'll subtract it. Okay, and that way, there's nothing on the left side, because I've moved everything over. Let's see, 0 equals, alright, now, we already said negative a squared and 2a squared makes 1a squared, or just a squared. Then there's a plus 7a that has no like terms. And there are two constants here now. Plus 9 minus 3 makes plus 6. Phew, and if at this point, let's say you mistakenly moved everything to the left side. I think if you had moved everything to the left side, you'd be left with negative a squared minus 7a minus 6. And you might have said, oh shoot, I moved everything over, but now the leading term is negative, and I remember that's bad. You can just kind of start over and move everything the other side. Say, oops, I guess I moved everything to the wrong side. Oh well. Let me start over and try to move things to the other side. Yeah, so not a big deal. If you move everything to the wrong side, just try it again. Erase what you did and move it to the other side. Okay, now that we have it all factored and pretty, I mean, we don't have it factored, so we have it all nice and pretty on one side, I'm going to have to factor it. Okay, and since each of these, it's a trinomial with leading coefficient 1, I'm able to factor it the old-fashioned way, where I just look for the numbers that multiply to 6 but add up to 7. That'd be 6 and 1, right? 6 times 1 is 6, 6 plus 1 is 7. Whew, and we almost have it. Now, I set each little factor equal to 0, and those will be my solutions. As long as they weren't among the values that I found in the beginning, that would make the denominator 0. Let me see, here I'll subtract 6 from both sides, and I'll find that a is negative 6. Alright, that's one solution, or potential solution, as long as it's not one of those guys I found to begin with. The other one, I'll subtract 1 from both sides. Okay. And that'll give me a equals negative 1. Okay, I think these are the solutions, but let me go back and look at the first step we did. What were the values that were bad? Oh shoot, sorry. There we go. Oh, look at that, step 1, way back up there. It was here. Where is it? A equals negative 3, which we don't have, so that's good. But negative 1 is bad. Uh-oh. I better throw that guy out. He's no good. So negative 1 is not part of my solution. He's out. So the only guy is negative 6. It looked like there was going to be 2 solutions, but there's really only one. That's sad. Whew. Alright. Well, these are tough problems here. But I think you guys can do it. You guys are go-getters. As long as you're careful, be really careful, you know, write, like I said before, write really large, because I think if you write small, you can easily mistake your handwriting and write the wrong number, or mistake this for that. And write really neatly, don't write too fast, because then it's easy to mistake a plus for a minus, or a 2 for a 7, or something silly like that. And take your time, put parentheses where you need parentheses, don't forget those guys, they're very important. But other than that, I think you should be fine. Just take time to practice, and I think you'll be good. Whew. And if you don't enjoy this, don't worry, there's only one more section in this chapter left, and then we'll be done. Move on to way simpler things. I think you'll like the next topic. It's a lot simpler. But thanks for listening. Sorry this video was so long. I kind of wanted to do a lot of examples, so I think every time you see an example, it makes a little more sense. So hopefully by this time, now that we've done a lot, it makes, enough sense to where you feel comfortable trying them on your own. But thanks for listening. I'll see you in the next video. Have a nice day.